So now that we've thought about our simple basic circuit concepts, let's now look at the direct current circuit, or DC. This is what we mean when we say DC. If I had to define a DC circuit, I'd basically say it's a case where a battery or power supply, it doesn't have to be a battery, creates current that only flows one direction. So it's not necessarily that the current is constant. It can actually go from 0 up to some value and it can decay back down to 0. But it always goes the same way, never goes back. That's how we distinguish DC from AC. So let's draw our simple circuit again and see what else we can begin to think about. So here is our battery and here is our resistor. And one thing we want to do different is what we call what the battery creates. It actually creates, the word for it is an electromotive force. What? That sounds strange. A force? We have to call it a force? Well, it's sort of an old-fashioned word. That's the problem. So the electromotive force, or the EMF, which the symbol is like this script E, this large script E, is the electromotive force. And you can kind of think of it, it's sort of an old-fashioned word. It's not so accurate, but it's the force to move electrical charge. There you go. Electromotive force. Okay? It's VBAT, right? So when we talked about our intro idea of a circuit, it generates some potential difference, delta V of the battery. That's all the EMF is. Right? So you have 0 volts down here. You just define one side as ground or as 0. Then you have E volts on this side of the battery. So it's really nothing new. It's just some terminology you'll see when you work on circuits. Everything else is the same. You're going to have a current flow this way because this is the positive side. The current is going to be equal to the EMF, the voltage out of the battery, divided by the resistance of the circuit, R. That's the same. And the voltage drop across R is going to be equal to, in this case, E. So if this side is at E and this side is at 0, the voltage drop is just E. Okay? So, but we can also get more realistic. This is a very ideal circuit here. Oh. It's ideal in a few ways. Some we've talked about. One way we've talked about how it's ideal is it assumes these wires are perfect conductors. We didn't have any voltage drop across the wires, so we've dealt with that. But another way it's ideal is it assumes that the battery or the power supply or whatever is supplying the voltage is perfect, that it always gives you the EMF. No matter what you do, you always get the EMF. That's not always the case. So we can also look at something, I can't write A's today, something more real, okay? So we could say here is our battery, but actually inside any battery there's some resistance. If this is a bunch of electrochemical plates in some nasty electrochemical medium, the plates have resistance. The current can't flow out of that battery without encountering some resistance due to something. Ions have to flow through solution. So actually, every power supply has a little bit of resistance built in with it. So we'll call that little r. And really, then you've got to think of this as the power supply. It's an ideal, you can imagine an ideal source of EMF plus a little resistor. So a little r, we'll put an S on it for the source. Okay? And then it goes around, and then there's the resistor you meant to put on there, what we've been calling big R. Now we'll call it big RL for load. Okay? So now, if we analyze this circuit, something kind of interesting happens. We have that the EMF by Ohm's law will equal I times the resistance, and the resistance in this case will be the sum of the two. We're going to get into how to add resistors and the reason later, but for now just trust me, this is R source plus R load. Okay. Well, then you could ask, what is the voltage drop you're going to get out of this thing if you think of it as an instrument? Well, what you're going to get is delta V, delta VR, delta VRL, and basically it's going to be the full EMF of the battery minus the current times R little s. Right? Because the full EMF drop is here, you dropped a little bit already over the resistance of the source, and then the rest drops over the resistance of the load. So you might say, okay, that's not a big deal. Just every battery, you know, you lose a little bit over RS, so instead of a 9-volt battery, it's an 8.5 volt battery. But what's unusual is it depends on the current. See? It's not a constant amount of voltage you lose. The amount of voltage drop you lose from the battery depends on how much current is flowing, which depends on our load. Okay? So no power supply or no battery really is a truly constant source of EMF. It actually depends on what it's doing. When you just have a battery open to the air and R load is infinite, you get no current flow, and then you get the maximum. You do get the EMF. But when you're actually running a circuit, that EMF goes down. So if you have a battery or power supply and you measure its voltage with some really high impedance, we'll say, meter, you get a high voltage. When it's powering some circuit with a lot of current, it actually might be lower. So just one of the many examples of how real circuits are not the ideal things we're going to describe through most of the class. So anyway, now let's move on to some more complicated circuits.